6 proofs of Gaussian integral. In this video, we are going to use 6 of these methods to prove the Gaussian integral. Let's start with the gamma function. Integral from 0 to infinity of e to the power minus x squared dx. Before we begin, it's important to know what gamma function is. So basically, gamma function of m is just m minus 1 factorial for natural numbers, but for other, it's integral from 0 to infinity of e to the power minus t to the power m minus 1 dt. By the way, this integral will just give you the m minus m1 factorial, and you can see that by using integration by parts. You will get a recursive function and then you will get this result. Yeah, it's just a generalization to real numbers of factorial. Now if we know this, we can solve this integral. So first of all, we will try to bring this to this form. So here we need minus t only, so let's substitute t equals to x square. That gives us t to the power half equals to x, which gives us half t to the power minus half dt as dx. Yeah. Now if we have that, we can solve it now. So since t is x square, square of 0 is 0, square of infinity is infinity, e to the power minus t, and dx is half t to the power minus 1 by 2 dt. Half can be taken out. Integral from 0 to infinity of e to the power minus t to the power, this can be written as half minus 1 dt. Now they are in the same form with m being half. So this is 1 by 2 gamma of half. What is factorial of half minus 1? So basically this is minus 1 by 2 factorial. Yeah. This is not really making sense for most of us, but through integral we can find that out. Or also we have a reflection formula of gamma function, that gamma n gamma 1 minus n equals to pi by sine n pi. We can use this formula to find gamma of 1 by 2. So if n is 1 by 2, this will also be 1 by 2, and this will be pi by sine of pi by 2, that's 1. Yeah, so gamma half is basically root pi. So 1 by 2 into root pi, that's root pi by 2, and that's the answer. This integral is equal to root pi by 2. And if this integral goes from minus infinity to infinity, yeah, that will be just double of it, since this is even function. That will be root pi, and it's a well-known result. So this is our first way using gamma function. Let's go to polar coordinates. Yeah, let's go to polar coordinates. We have this integral. Now for polar coordinates, you will need to have double integral. Yeah. So first of all, let's square this so that you will have two such integrals. But there's no use having two such integrals in the same variable. That's why we will change this dummy variable into a different one. Now we can just merge these two integrals. That's allowed. E to the power, and use power law of indices to get such function. Now we will try to change x, y variables to r, theta variables. That's from Cartesian coordinates to polar coordinates. Now let me give you some idea on how these two work, and these differential elements work. So basically dx dy. Dx is just differential element that moves in x-axis. Yeah, these are dx. And dy are differential elements that move in y-axis. Yeah. And now r. So basically r is any, like x is any point on this coordinate, yeah, y is any point on this coordinate. So r is basically of the length r, there are many points over here, yeah. So basically r encompasses these things. So dr includes these points which are at the length of r from the origin, yeah. And d theta is just the change in angle, yeah. So r, let's say r is this line, and d theta is just a small change in angle. So dr d theta, let's say this is delta r. Delta r means the change in r vector, and this is del theta. So dr d theta is just this area. They can say it that way. So this was the introduction of these differential elements, yeah. And now we will try to see, like okay, first of all let's like see their relations. Okay, first of all let's see their relations before we begin. Basically r square equals to x square plus y square, and theta equals to tan inverse y by x, yeah. And our x is r cos theta, y is r sin theta. Now it's necessary to find the limits of integration when we take dx dy to dr d theta, yeah. It's necessary to find the limits of integration, and also how dx dy will relate to dr d theta, yeah. How dx dy will relate to dr d theta. So it's important to find these things, yeah. And now let's try to find the limits of integration. How do we find that? So basically we need to be able to cover the same area as the dx dy covers when going in these limits. This is just the height of the height of the 3D shape, and this is the area, yeah. So now our x is going from 0 to infinity, and y is also going from 0 to infinity, yeah. And over here, for every y value, for every y going from 0 to infinity, x will go from 0 to infinity. That means, let's say there's a small dy that y is going in y direction. Now for every dy, there will be all this dx that will go from 0 to infinity, yeah. There will be all this dx that go from 0 to infinity. Now again, for next dy, there will be all this dx that go from 0 to infinity, yeah, and so on. Again, for next dy, there will be all the dx going from 0 to infinity. So basically, we will cover all of the first quadrant, yeah. So this dx dy in this limit range covers the first quadrant. Now we need to be able to cover first quadrant using dr d theta as well, yeah. Now let's go to dr d theta. So let's say for this r, let's say this is 2. For this r will basically go from, this is a dr. So this r will just revolve around in this circle based on what theta is, yeah. So for this value of r, theta needs to go from 0 to pi by 2. So this is one of the dr d theta, this is another dr d theta, yeah, this is another dr d theta, and so on. So basically, so this is a dr, this is the dr. Since this is a whole r, yeah, this is a dr, and dr is going from 0 to pi by 2. Again, this dr, it will cover in this way, yeah. Now again, for this dr over here, it will go in this way based on theta is pi by 2. So for this to cover, our r should go from, like 0 to infinity. Yeah, so for all of these boxes, so okay, so for let's say if this is length 10, so at length 10 our dr will be going like this based on theta. So r should go from 0 to infinity itself, and theta should go from 0 to pi by 2. Yeah, so that is a thing. Yeah, and now let's try to solve this integral. And yeah, now the limits we know, that is let's write over here dr d theta, and r is going from 0 to infinity, theta from 0 to pi by 2. Now, but how exactly these two are related? To find this, we need to have Jacobian matrix. Yeah, so what Jacobian matrix is, let's say if we have to find, if we have to take dA dB into dm dn, we will have a determinant over here which will be determinant of AB with respect to determinant of mn. We will have this thing, and this can be found out by dA by dm, dA by dn, yeah, dB by dm, dB by dn. So we will use this determinant to find this determinant, and then dm dn. So we'll use this thing. Now let's do that. Now our dx dy will be equals to dxy by dr theta times dr d theta. This will be equals to dx by dr, dy by dr, dx by d theta, dy by d theta times dr d theta. Now x is r cos theta, so that's why this will be cos theta. Y is r sin theta, so this will be sin theta. X is r cos theta, so that will be minus r sin theta. Y is r sin theta, so that will be r cos theta times dr d theta. Now if we find the matrix, this will be r cos square theta plus r sin square theta, so that's r only, r dr d theta. Now let's be back here. So dx d theta is actually equals to r dr d theta, and then e to the power, here was minus x square plus y square is just r square. Yeah, so we have reached this point. Now it's really easy to solve from this point. Yeah, now here's e to the power minus r square. So over here we will try to make d of r square. Yeah, or let's just use U-substitution to make it further easy. So if we substitute u equals to r square, what will happen? Du will be 2r dr, yeah, and then du by 2 equals to r dr. Now after this we will have integral from 0 to pi by 2, and r square will go from 0 to infinity, and then over here we will have e to the power minus u, and then du by 2 d theta. So now 1 by 2 can be taken out, integral from 0 to infinity, 0 to pi by 2, sorry. This is e to the power minus u by minus 1 from 0 to infinity of d theta. This will be equals to 1 by 2, integral from 0 to pi by 2. So this is e to the power minus infinity is 0, and then minus minus plus, and e to the power 0 is 1 d theta. Now 1 by 2, this will be theta going from 0 to pi by 2. That gives us, this is pi by 2 minus 0, so pi by 4. Yeah. Now this was I square, you know, this was I square. So I square equals to pi by 4. What does that mean? I is root pi by 2. That's the answer. So over here it's the same answer, yeah, root pi by 2. Now let's do it by visual method. Visual method is quite easy. Basically we had found out that this is actually equals to integral from 0 to infinity, integral from 0 to infinity of e to the power minus x square plus y square dr d theta. Now I told, sorry, not dr d theta, dx dy. Now I've told you that this dx dy actually encompasses the whole graph. Yeah, but for let's for the sake for now, let's try to find from minus infinity to infinity, yeah, for now. Let's do that, and in that case it will encompass the whole graph. Yeah, now this height, so this height will actually be graph something like this. So over here we will also need to have a z direction. Yeah. So for that the graph should be modified, somehow modified for z direction. Okay, so let's draw the graph like this. Okay, now this the graph of this function will something like this. From 1, this will come out in this fashion, in every direction. Yeah. Okay, and these are circles. There will be circles of this form. If you try to like see it through distance or something like this, there will be circles, and these are going in every directions. So basically, like our radius from the center, for this radius over here, we can find the volume of this thing, this circle, or let's say a differentiated circle, or just some part of the circle. This is, let's say, cylinder. Now when it goes further away, we can find the small part of the next cylinder. So you can continue finding these volumes, and then we can, like, these will be the same as this integral. So basically the volume of this cylinder will be this circumference times the height. Height is this thing. Now this thing, if this is the r, this thing will just be e to the power minus r square. Yeah, x plus y square is just r square. This is the height. Yeah, and now this integral can be written as r is going from 0 to infinity. Yeah, and the perimeter of this cylinder, this perimeter will just be a 2 pi r. Yeah, and 2 pi r times dr, that will be just 2 pi r, since this whole length times this dr will give us this perimeter. This is not actually perimeter, this is a two-dimensional thing, but just let's say a strip or something like that. So that will be 2 pi r dr. Yeah, 2 pi r times this dr. And now the height is e to the power minus r square. Height is r square. This is the height. Now we can find this integral as well. This will also work. And now this will be, take 2 pi out, integral from 0 to infinity of e to the power minus r square, and then r dr. Yeah, so now this will be, just put 2 over here. Now this will be integral from 0 to infinity of e to the power minus r square d of r square. Yeah, so that will be e to the power minus r square by minus 1, and there is a pi going from 0 to 1, so that will be pi times, this will be, it's going from 0 to infinity, so 0 plus 1, so that's pi. Yeah, now the I square is actually equals to pi. Yeah, and so I equals to root pi. But over here, our I is going from minus infinity to infinity. Yeah, I is like that. So that's why integral from 0 to infinity of e to the power minus x squared dx will again be root pi by 2. So that was a geometric proof. Now let's go to next proof. U-substitution. Okay, for this one, but this is also kind of similar though. We know that I square will be integral from 0 to infinity, integral from 0 to infinity of e to the power minus x square plus y square times dx dy. We can substitute y as xt. Yeah, we can make the substitution, and that will give us dy equals to so if we substitute y as xt, we will have dy equals to t times dx. Okay, so if you substitute y as t times dx, yeah, but you want in terms of t, yeah, but over here you want to change it to t, so that's why x will be constant for some time, so you will have x times dt. Now after that, when y goes from 0 to infinity, you want to find out what t goes from. Yeah, so okay, so t will just be y by x. So when y goes to 0, t will go to 0. When y goes to infinity, t will go to infinity. Yeah, so that's why now integral from 0 to infinity, integral from 0 to infinity of e to the power minus, over here we will have x square plus x square t square, and then dx is dx itself, and then dy will be x dt. You can just take the x inside, doesn't matter. Now let's continue it over here. We had integral from 0 to infinity, integral from 0 to infinity of e to the power minus x square 1 plus t square, and then x, we can write that inside, and we can also change, since these are just same constants, we can just change, we can make it dx dy. Now for this, what you can do is you can just introduce the derivative of this term. You can just introduce the derivative of the term over here, to the power minus x square 1 plus t square. That will be derivative of x square 1 plus t square. You can introduce that, yeah, and then introduce some constants. Okay, so this is not y, by the way, this is dx dt. Introduce some constants, which will be 1 by 2 times 1 plus t square. These are the constants, yeah, which is not in the x world, yeah, and then dt. Okay, so now if we do that, integral from 0 to infinity of 1 by 2 times 1 plus t square, and over here this will just be e to the power minus x square 1 plus t square by minus 1 from 0 to infinity times dt. After that, we will have integral from 0 to infinity of 1 by 2 times 1 plus t square, and this will be at infinity, this is 0, at 0 this is 1, and so that's just 1 times dt. Now this is 1 by 2 times tan inverse t, going from 0 to infinity, and this is 1 by 2, pi by 2 minus 0, that's just pi by 4, which is I square, so I is again root pi by 2. So this was another proof. Now let's go to next proof. Next proof is from Ramanujan's theorem. So this is quite similar to gamma function. So Ramanujan's theorem states that this states that if a function can be written as sum from n going from 0 to infinity of minus x to the power n some function phi of n by n factorial, then the integrals from 0 to infinity of x to the power m minus 1 f of x dx will just be gamma of n times phi of minus m. So this is Ramanujan's master theorem. So now for this integral 0 to infinity of e to the power minus x squared dx, first of all we have to make this as m. Yeah, we have to make x squared as m, and that gives us e to the power minus m. Yeah, e to the power minus m to the power minus 1 by 2 dm with 1 by 2 in front, just like when we did the gamma function problem. Now over here we have m to the power minus 1 by 2, which is 1 by 2 minus 1. Let's write it as x, that will be easier. E to the power minus x, and we will have x to the power 1 by 2 minus 1 dx. Now we need to find the series of e to the power minus x first. Series of e to the power minus x is sum from n equals to 0 to infinity minus x to the power n by n factorial. Now for phi of n, we just have 1 over here, so phi of n will just be 1. Yeah, and now by Ramanujan's master theorem, this should be equals to 1 by 2, and then gamma of m is 1 by 2, and then phi of minus 1 by 2. Is it? Yeah. Now phi of any number is just 1, so that's why it's 1 by 2 into gamma 1 by 2 into 1, and we know gamma 1 by 2 is just root pi, so root pi by 2 is the answer. It was mostly same to the gamma function solution, but just that this has a new name, which is Ramanujan's theorem. Okay, here's the problem. Now reverse Feynman technique. Now let's go with this idea. Okay, now for reverse Feynman technique, we'll again introduce I square, which goes from 0 to t, 0 to t, and then e to the power minus of, let's write it as I of t. So we will need a new integral I of t, which goes from 0 to t and e to the power minus x square dx whole square. Yeah, we are going to use this integral to make some manipulations, and at last we will find out I of infinity and then a limit. Let's write it like this. We'll find out I of t, where limit t goes to infinity, yeah, and the square root of this limit will be our answer. Yeah, so let's deal with this. First of all, we can try to differentiate this di by dt. So 2 times integral from 0 to t of e to the power minus x squared dx. Now d of dt, let's try to differentiate this with respect to x, let's say, or but this need to be done with t. Yeah, okay, wait some time, just wait. Yeah, okay, fine. Okay, now we have one theorem from fundamental theorem of calculus, that is, if we are differentiating something of integral from 0 to t of f of x dx, yeah, this will just be f of t. Yeah, this will just be f of t, or rather this should be something like this, something like f of t, yeah, and then dt by dt. Yeah, if here is a of something, then we would have f of a of something, and dA by dt minus we will have f of 0 d0 by dt. It will be something like this, so that's why it's f of t. So this will be f of t. Yeah, so due to that we will also have over here what will we have? Okay, let's erase this. Okay, so over here, since we are integrating and this is differentiating the same thing, we will just have e to the power minus t square. Yeah, to the power minus t square. Okay, now we can bring this constant inside the integral. Di by dt will be 2 times integral from 0 to t of e to the power minus x square plus t square dx. Now to make this limit simpler, you can define something like this: x by t equals to u. Yeah, x equals to ut. If we define something like that, it will be di by dt equals to 2 times integral from 0 to 1 e to the power minus x square plus t will be u square. So mu was now t equals to x by mu. Is that now x equals to mu t? Let's substitute x instead of. Okay, now x equals to ut, so that will be u square t square plus t square, and then dx will be okay. So we are going to the world of u. Yeah, so we are going to the world of u. So that's t du. So dx will be t du. Now for this, t will be constant since we are trying to go in the world of u. Yeah. Now after this, we will have di by dt equals to 2 times integral from 0 to 1 of e to the power minus t square u square plus 1, and then okay, did I forget something here? Okay, I did not. Now for this we have t. Yeah, now if we try to make it something like 2t times minus 2t times u square plus 1. If we write this over there, and then of course write something as the product, and then of course after this we need to write 1 by what we have just written, 2 minus 2 times u square plus 1 du. You can write it something like this, and there's a reason for doing that as well, which is di by dt equals to 2 times integral from 0 to infinity. This will be d by dt of e to the power minus t square times u square plus 1, and du by minus 2 times u square plus 1. Now we can take d by dt outside, which is actually the reverse Feynman technique that's it's not named over, and there will not be any problems of convergence for this, but this one for this thing. And then we will have, now when it goes outside, we will have the normal derivative. These are also normal derivative, yeah, not the partial ones. And then 2 will also cancel out. Integral from 0 to infinity of e to the power minus t square u square plus 1 by minus of u square plus 1 du. Now tt will cancel out. Yeah. Now since here's a d and here's also di, I will just be this integral. This dd will also, let's say, not cancel out, but we can just see like that. Yeah, minus u square plus 1. Yeah, and then now this is du, and plus a constant. Don't forget that. Yeah, this is I of t. Now our I of t was also defined as something like this. Our I of t was also defined as integral from 0 to t of e to the power minus x squared dx squared. Yeah. So now I of 0 will just be integral from 0 to 0. Yeah, so that will be 0. Yeah, I of 0. Now from this integral from 0 to infinity, t is 0, so minus u square plus 1 du plus c. And I of 0 is actually 0, and this is tan inverse u going from 0 to, okay, this is not from 0 to infinity, by the way. This integral is not going from 0 to infinity, it's going from 0 to 1, by the way. I made a mistake. Okay, 0 to 1, 0 to 1, 0 to 1, yeah. 0 to 1, 0 to 1. Okay, now that's just minus tan inverse u going from 0 to 1, so that's minus pi by 4. Minus pi by 4 plus c. So that's why c equals to pi by 4. Yeah. So we know now that I of t is equals to integral from 0 to 1 e to the power minus t square u square plus 1 by minus u square plus 1 du plus pi by 4. Now if you find out I of infinity, yeah, that will be our required integral squared. Yeah, so I of infinity is this squared, so root of I of infinity is what we want. Now this integral over here, if we have I of infinity, if we want to find that out, so e to the t goes to infinity, so e to the power minus infinity will be 0, so whole integral goes to 0 plus pi of 4. Now I of infinity is pi by 4, the root of I of infinity is root pi by 2, which is the answer. Yeah, this is the answer, since this is the required integral. Root of this integral is the required integral. Oh yeah, we have solved this by reverse Feynman technique as well. Yeah, and so we have done it by all the 6 ways, and all of these gave a correct answer, root pi by 2. Thanks for watching, hope you enjoyed the integral.